Um, hello. Okay. That. Uh, uh, how are we doing? Okay. I think. Hello. 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 I think. Can you actually hear me? Yes. Yes. Hello. 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 Yes. Great. Great. I love it. I love it. Okay. Thank you. Hi. Okay. Oh, and could someone make a noise? Because I'm actually not sure I can hear you. Because I'm make a noise.
Hello.
That was awesome. All right, that was totally persuasive, articulate. I think it was even correct. I think that. All right, so we can hear each other stuff. I'm not on headphones. I may have to switch my audio in the middle of this. Something blah blah something. But we are going to. Okay, pardon me for 1 second. But we are going to move along. We're going to keep doing what we're doing. I think. I think people are starting to get 50-point things back, and more as the problems get thicker, you'll be getting them back in the middle of class. Like whenever you submit for 50 points, I'll put in the new portals while we're talking. But anyway, we're moving on. Oh, I want to ask one thing to make sure I'm not crazy. What are you up to? What can someone just quickly, either in the chat or in voice, just tell me where the very last thing you no, let me rephrase it. What's the very next thing that's due in lab for you guys?
Post lab 3.
Post lab 3. Okay, thank you both. Okay, and lab 3 is, dare I say, the wave. Lab 3 involves waves. Yes.
Yeah.
Okay, the post. Okay, so that's great. That is very helpful. Up and thank you. Okay, I see it in the chat. Thank you. That's totally helpful and good, because it means what I'm trying to do here. I don't know if you'll see. I'm saying this to everybody. What I'm trying to do here is absolutely the material that connects up with lab 3 to together. They are what are hopefully going to get us to all understand wave motion. Like that's the idea here. It may not seem right now at all that what I'm talking about in class is related to lab 3. Hopefully by today you'll see how it is, but that's good to know that that's where you are, because that is where I am in my head. So hopefully, things might get, we might move along today, and some, even though the material will get harder or more advanced, I think some things will start being very clear to people. If and hopefully, oh, now that I know, you just told me, hopefully this will help you write and submit post lab 3. And you can definitely interrupt me once we're going here. See what we're talking about, all of you, any of you. You can definitely interrupt and ask.
Yes, I am.
You can definitely interrupt and ask a question about the lab. I would be happy.
I'm in it right now.
At the moment, if we could all mute or whatever. If I can't answer it, I'll say I can't, or right then. But it's only better if anything I'm saying can be hooked up and connected, make your life easier in lab. So feel free if you see any connections at all, to stop and ask me. But okay, what I want you to picture, like the problem that we're going to do here together as usual, and you'll answer blah blah blah. Remember, we started with this last week. We've been analyzing one oscillator for like ever, I know. Then we finally sort of have been trying to add a second oscillator to the analysis by means of that phase constant phi. Then, now it sounds like now we're just like pushing our luck, but in fact, no, now I want to go to a third oscillator, but really, I don't want to like dwell on 3 oscillators. Where we're really going with this material now is I want us to start picturing, literally picture in your mind, or picture doing a lab with equipment, picture a huge collection of identical harmonic oscillators, right? So like picture a long lab table that has a bunch of springs all piled along it. Each spring is, with a mass on the spring, and each spring is like vertical, which I believe was the case for your very first lab, but and doesn't change the physics at all. But just to make this easy to picture a vertical spring on the lab table, so it's free to oscillate up and down, and then one next to it along the x-axis, but also free to oscillate up and down the y-axis. Okay, so we're creating a 2-dimensional situation here on purpose. A large collection of oscillators lined up equidistantly along the x-axis. So like, the most uniform, simple, sort of obvious arrangement you could imagine, with identical harmonic oscillators. And then each one of them free to oscillate in the y direction. So just like what we've been talking about last Thursday and last Tuesday, but now like picture a bajillion of these, and picture that they're all nicely, so they're like 1 centimeter, you could even say, and here I'll draw a picture. Like you can even picture something like, these are supposed to be springs. I don't know why my springs are turning into like spider claws or some weird, but these are supposed to be springs. And you see what I'm trying to do. And if and one thing I just made an accidental mistake there. You know, picture a bunch of springs lined up on the x-axis like this, and each one being ready to oscillate along the y-axis. And picture, what I further want you to picture is, and every detail I'm saying here, every extra detail makes it more complicated sounding, but every detail I say is in an effort to sort of precisely assure us that it's the simplest, most obvious arrangement possible. What I mean by that is, like, we've got oscillators distributed along the x-axis. Let's make our life super easy and say that, like here, this oscillator that we're going to call oscillator number 1, right? Let's literally put it at the position x equals 1, like at 1 centimeter from some, designated 0 point. And then the next oscillator, which we can call, oscillator number 2, we'll put literally at x equals 2 centimeters or whatever. Okay, so imagine we've lined this up so it's like as easy as possible to talk about, to watch, to observe. Okay, and all the oscillators are identical, vertical oscillators. So if they're all identical, they're all going to have the same amplitude and the same angular frequency, right, omega. But like I was trying to say Tuesday and Thursday, like I was asking you to picture with a couple of oscillators or 3 oscillators, let's imagine that the one thing that's different about all these oscillators is exactly what I'm trying to draw, which is imagine that they're all released at different moments, right? Or they're released from different places, which is really the same thing, right? In other words, imagine that each one of them has a phase constant that's different from the next. And if you look back to your notes from last week, or you just picture a situation, like I could come up with any pattern I want, but I could come up with any interval I want, but let's all try to imagine and agree, like I'm going to picture some interval in my mind by which the phase constant will differ, but I'm just going to picture it as a number and make it no more complicated than that. In other words, you might recall on Thursday, we had a situation where one oscillator had a phase constant of pi over 2, and the other one had a phase constant of pi, like they differed by pi over 2. So then if we added another oscillator, we expected its phase constant to be 3 pi over 2. I'm continuing that same total pattern, that same idea of like, let's just have each one of these differ by the same phase constant. Sorry. What I'm trying to say right now is imagine that we did, well, actually, let me write. Okay, I'm saying, and again, I haven't asked the question yet, like this is the setup for the new situation. This is a fairly fundamental big situation. We'll ask a lot of questions about it. But I'm saying now, let's generalize the idea that we had on Tuesday and Thursday. Let's take a whole bunch of oscillators and say that each one differs in phase from the last one by pi over 2. Like I'm specifically choosing the number, and as an example, I'm choosing the number pi over 2. Like we could have done this with pi over 3 or pi over 4 or like any crazy number, but in this case, so we're saying such that every single oscillator is described by an identical equation. Like each one can be captured by an equation that differs only in this last term. And so the very zeroth oscillator, let's say the zeroth oscillator, would have a phase constant of 0 because we're doing this pattern of like n times pi over 2. The first oscillator would have a phase constant of 1 times pi over 2. The second one would be 2 pi over 2. That's what we're saying. So we're imagining. So in other words, if we create this situation, what's nice is we can have a whole bunch of oscillators doing different things, moving into kind of different ways from each other, but we can capture the whole thing with one equation that's like a rule that tells us how to generate all the individual equations. Okay, so I'm asking everybody to imagine that. Now I'm going to add one more thing to the imagination and then ask you a question about it. And I'll turn back if anybody wants. Right. Okay. So I'm shifting the equation. I still haven't asked a question, just to be clear. I'm still setting up the situation. I'm now shifting the equation slightly, or I'm saying, if you can picture the situation that I'm saying, and if you can picture how this, and I will stop. I know that I'm trying not, I know this is like a lot of talking to observe, whatever, but if you can see how this equation works to describe a whole n number of oscillators, like if you had 6 oscillators, so they went from 0 to, or 7 oscillators, so and ranged from 0 to 6, like this could simultaneously describe all of the oscillators in this arrangement, as long as you pick the end and I know which one you're talking about. Now I'm just elevating it slightly and saying, okay, now if we've really done this nicely and arranged the oscillators so that the first oscillator is literally at position +1 centimeters or +1 meters from the origin. And by the way, we can even number in the back and say that, anyway, if we number them nicely like that, then we can actually make this equation one that has y's and x's in it instead of y's and n's. We can say, oh yeah, like x equals n. If you're the first oscillator, you're at position 1 meter. If you're the second oscillator, you're at position 2 meters. Therefore, we can rewrite the equation this way. Okay, all I've done is change the n to an x. All I've done is change the n to an x, except now this is starting to look more like physics, frankly. Like physics doesn't usually count objects. It makes a prediction about a system or an object. So now we've got an equation that has y and x in it. The first question I want to ask everybody, anybody, here's my first, and it's actually a quick, this is, you might get this very quickly. This doesn't take a lot of work, but the first question I want to ask anybody or everybody is what are the units of that? Like, there's a pi over 2 there. That's so fast and so good. Now I'm going to say it's really cool that that was so fast. Oh, and I'll repeat the question. And it's almost right. I'm going to give him another moment. I think he wants to add something to that to make it fully right. Clearly the right track. But so I'm asking everybody, just to be clear on the question, but that's awesome. That is, and obviously that's 50 points, whether it's right or wrong. Actually, it's especially, even if I'm sort of saying that's not quite right yet. But I'm asking everybody, yes, what are the units of this pi over 2 term? This is a term, if this equation is a valid equation, and if it spits out what it should, something entirely in meters, then the pi, here we go, getting closer. This is awesome. Both of them, they're, yes, it's over something. It must cancel out something. You're both, yes. Okay, this is, okay, I'm sorry. This is what I mean, it's like, why don't I just go, do the, yes, like this is about as exciting as class can be for me at this point. I think you guys just progressed toward the answer. I think you progressed. I think you didn't know it at first and you got yes. And by the way, right, other people should be yes. If you're figuring it out now, definitely put it in and it's points. And I don't care if someone already said it. It's definitely not a race or a competition, but it does make me excited to see how the answers sort of progress from almost there to there, especially in the same person. I hope everybody feels good. Yes. That's what, okay, that thing must be in those units. I'm not even going to, Well, yes, I'm agreeing with that. And all of you who just put that in, really, really, even if right now you're sitting there thinking like, okay, I don't get what's going on at all, but I guess that's the answer. And I guess he's saying if I put that in right now, I then can write it up for 50 points. Yes, I am saying all of those. Hopefully, then if you're going to put it in, you would then stop and make sure you know what it is answering. But yes, now this is important. We are all, I'm going to believe now we're all kind of hearing each other and saying that this pi over 2 isn't just radians, it is itself radians per meter. It's signifying something. It's like a step or a rate in a graph. If you think about it, like it's saying for every x that you go over in this arrangement of oscillators, for every amount x that you move your eye over and look at this arrangement of oscillators, or for every x that you choose which oscillator to look at, we're going to advance the phase constant by that many pi over 2's, right? Like if you like shift your eye two down the line, then you're going to see 2 differences of pi over 2. If you shift your eye 3, if you look at 3 oscillators, if you look at 3 meters later down the line of oscillators, then you're going to observe a phase constant shift of 3 pi's over 2 radians. So absolutely, this thing is like a rate, if you like, a rate or a density of radians, measure of radians of phase constant shift per unit length, per meter across the x-axis. So this is a constant. This is, so hold on. That's very good, though, the people that said that, just like. Okay, so one thing I'm saying right away is that pi over 2, what you're noticing, once you notice or realize, convince yourself that that pi over, if you agree, and this is what I'm saying so far, that we could collect a whole bunch of oscillators together and have them move in a kind of complicated motion, but capture the whole arrangement in one equation. That's what I'm saying so far, that our equation for oscillators is like powerful enough that it can embody a whole collection at once. And if we wrote it in the way that we're writing it, and if we arrange things the way we're arranging them, then in the same way that we've been believing in this kind of rate that describes oscillators, this rate in time of cycles per second, which we call, or which we then measure in radians, because there's 2 pi radians in every cycle. So we've been watching through and paying attention to this rate in time called angular frequency, omega. It measures radians per second. Well, what we're now introducing, what the pi over 2, which is just an example, pi over 2 is functioning like another rate happening at the same time, but this time a rate in space. This is now how many cycles we complete, not per second. This is like tracking how many cycles or portions of a cycle, radians, not how many radians we move through every unit of time, but how many we move through as we progress across space, specifically the x-axis. So pi over 2 is an example that we're looking at right now, but however it's functioning in our equation is this, it's like the space version of how omega has been functioning all along. This is the space counterpart to the role played in time by omega. There's going to be a name for this, of course, but right now, so it's some kind of rate cycles per space. I'm going to go to the next page. Hold on. So it's a little while again before the next question. Sorry, I don't want to be talking so much. I do want to ask a question, but oops, sorry. What one way to understand this pi over 2, right? Now I'm using pi over 2 as an example. I'm saying imagine that we stagger these oscillators by phase shifts of pi over 2. And it's really like saying, imagine that we're staggering each oscillator by a quarter cycle. That's what we're saying, right? So they're all a quarter cycle ahead of the next guy or a quarter cycle behind the next gal. Well, another way of understanding that, if you think about it, is if you made a graph of their phase constant as a function of x position, right? We put phi in radians on this axis, and we put x in meters on this axis. If we made a graph, like if you're at position x equals 0, then you have a phase shift of nothing, of 0. So that's the point at the origin. If you go over 1, you go up pi over 2. If you go over 2, you go up 2 pi's over 2, right? In other words, if we made a graph like this, it would be a straight line graph. The phase constant is a linear function of horizontal position, and the slope of this graph would be that number, pi over 2. That's what pi over 2 represents. Pi over 2 equals the rise over the run of this graph. Measured in radians per meter. So it could be anything in any situation. It could be anything. In this case, it's pi over 2, but it has a name. This thing, this slope, is what we don't call it angular frequency. We call it angular wave number. And the reason we call it angular wave number, whatever this number, the number that happens to be pi over 2 in this case, the slope of the phi x graph is called angular wave number. We call it angular wave number because, as you may well have guessed or understood a long time ago, if we put a bunch of oscillators this way, if we take a huge collection of identical oscillators, allow them all to oscillate along one same axis, but arrange them all on a different axis. And if we do nothing but stagger their phases by a constant amount, a constant step, which we are going to call angular wave number, okay? If we take a bunch of identical oscillators and stagger their oscillations by this thing that we call an angular wave number, then what the motion that we get, I'm sure you can already see, or I think you can see, or this is the point of lab 3, the motion we get is wave motion. This is what a wave literally, absolutely, fully actually is. That is to say, for a wave pulse, when you say, oh, a wave traveled from here to there, like you're standing at the beach, standing at the water, and you're watching the waves come in. I mean, it's like the most real life wavy thing that can happen, like outside a lab or whatever. You're literally watching waves come in, and you can say things like, oh, a wave is coming in now, or like, oh, wait, there's a big one coming, or hang on a second and get my surfboard, or whatever. Like you can literally say, oh, the wave is coming, and then you can talk about, oh, the wave is gone now, or the wave is here, right? Like it's a thing that you can track with your eye. And if you track that wave pulse coming in, what is it that you're really tracking? What are you talking about? Well, you're talking about water for sure. If we're at the beach, we're seeing a water wave come in. But now let's think this through really for a minute. When you say a water wave is coming in, the reason you're calling it a wave, and the reason you're not just saying, oh, a bunch of water is like being thrown at me, is because you actually know in your mind, as you see this wave coming in, that there's no water actually moving towards you at all, right? Like all the motion is happening toward you. And this is a heavy point. This is what we mean by waves. So I'm taking a step back for a second from the math to remind us like what anybody means in wave in real life is a weird thing. When they see a water wave coming in, what they're saying is something is coming in that I can totally track with my eye. I could probably track with a ruler and a stopwatch. They can. Like I can predict its motion like I could a baseball or a cannonball or whatever. So I'm tracking this thing that's coming in that's totally made of water. And the only things that are moving for sure are water molecules. Clearly, there's water moving. And the motion is toward you. But you know, if you think about it, there's no water actually moving toward you, right? Like everybody knows when they stop and think about what you picture when you picture wave ripples is there's a bunch of water over here going up, down, up, down. And then there's a bunch of water over here going up, down, right? And more specifically, it's like up and then down. And then this one goes up and then down. And then this one goes up and then down. So what you see coming toward you is like the shape of water. You see a hump coming towards you, but everybody knows it's not a cartoon. It's not literally like there's a mountain of water that's like skating along horizontally toward you. Put it more scientifically, there's no water molecule at all that is making the journey from where that wave started to you, even though something clearly is moving towards you, like something that you could ride a surfboard on or something that could crash you in the face and make you go under. Something comes in, it's entirely made of water, but no water comes in. And you know that, right? Like I'm not trying to blow anybody's mind by saying that, but I am actually trying to say, now hang on, that is a weird thing. In fact, let me write specifically on the next page. What wave motion is in English, just in normal terms, when anybody calls something a wave motion, what they're really saying is it's motion of something, but there's no something doing the motion at all, right? Literally, and I'm going to write that in better terms in a moment for everybody. And it's not a digression. I'm trying to say what it is a staggered oscillation that you're seeing. But when you see water coming in at the ocean, you are right to say that something is physically moving through time and space. Like something was there, now it's here. It took a certain amount of time. That was a certain amount of distance. Like we can put a speed to it and everything. It's total real scientific motion. A wave ripple comes in to your face. The only thing that is doing any motion at all is water molecules. Like that is also fair to believe and to say. But let's be clear, if it's a wave that's coming into your face, a water wave at the ocean, then even though the only thing that's doing any motion are water molecules, there's no water molecule that takes that trip along to your face. In other words, no water molecules need be moving along the x-axis at all, even though all the motion is along the x-axis, all the motion you observe. The collective pulse moves along the x-axis, but only because a bunch of little water molecules were in their places, all in a line going up, down, up, down, up, down. Like it's just, right? Like that's what a wave really is. What a wave really is this collection of staggered oscillators. So wait, first of all, I know I haven't asked a question, but let me just write down a definition just so I can make this clear. Okay, this is my definition in English. I mean, bad English, but this is my like non-mathematical but honest definition of what we mean by wave motion. Whenever we talk about waves in a regular world context, casually, or in the physics context when we're really studying them, either way, what it is we mean when we talk about wave motion, I just want to make this clear, like right here, we mean motion of things that aren't things. Like really, when we say wave motion, when we say a wave moved from here to there, what we really mean is some motion happened from here to there that we can totally scientifically measure and predict and analyze and believe in all respects, but for which we can identify no single object in the universe that necessarily went from here to there. Like when a wave goes from here to there, what we're saying is there is no thing at all that is moving from here to there. No thing. It's like an unthingy thing. And really, that is, and that's weird at all. Like I want to emphasize that because I still find that very, frankly, I do want to blow your minds. Honest, like in my fantasy, your minds would be blown by that because mine still is all the time when I think, how is that even possible? It's just so weird that we believe in these motions that don't actually have movers underlying them. We believe like that heat goes from here to there, but there's no like hot thing that go, or better yet, the more example of what I'm talking about is somehow I'm talking to you guys right now and you're hearing me, like, and forget about all the internet and all that. Like, even if we were in the same room, I'd be talking and you'd be hearing me, which means something's going from my mouth to your ears. We all believe that, like something goes from my mouth to my ears, and we all even understand that somehow there's air between my mouth and your ears and the air is vibrating in a certain way. So I guess air molecules are moving such that sound goes from my mouth to your ears. But you have to be clear, we all have to be clear that even though the only things that are at all possibly moving such that you can hear me are air molecules, there's no freaking air molecule that is traveling from my mouth to your ears. That would be gross and inappropriate. Like that is not the point of me talk. Like we don't want that. In fact, that's why we're on the internet, because we really don't want that. And it's true. Something can go from me to you without anything going from me to you. And that's called wave motion. That's what we're really here to study. That's why I'm talking too much about it, but it really is the point of this course. Now we're finally there, kind of like we're now at how we can see how a phenomenon can embody motion and produce motion, but it's a whole phenomenon. It's a dance of lots and lots of little particles. No one particle could do it. In order to make a wave, what we have to make is an equation that, in order to mathematically now analyze a wave, we write an equation that will embody necessarily a whole collection of identical oscillators, all identical harmonic oscillators, but all in staggered phases. That's what a wave actually is what I'm trying to say. So I'll say that. I'm sorry, it's still not a question. It's just me talking. I just get too excited about this. But this is like the point. This is like, and what you're trying to see in lab. And it still doesn't connect. It may, well, anyway, we're still going to connect it. What time is it? Okay. Oh, actually. Okay, in principle, in general, then what I'm saying is what a wave is this thing where motion happens from here to there, but no individual particle travels from here to there. Like again, that's what wave motion is. It is distinct from particle motion. It's a phenomenon, it's a behavior. It is not an individual trajectory. how to make a wave or how to understand how a wave comes into existence or whatever is what we're talking about now in lecture, is you take a bunch of identical oscillators. And every time I say identical, what I really mean is same K and same M, or if it's any other kind of oscillator like a pendulum or anything, then same equivalent parameters such that it has the same omega. Like, I mean, same parameters, same material properties such that angular frequency is the same. And that's usually easy because that just means use one kind of material. So a wave motion comes about when you have a whole collection of identical harmonic oscillators that distinguish themselves from one another in the simplest way possible. They each have a phase that is staggered by, in the simplest possible case, our case, a constant amount, right? And yes, I will ask a question in a moment. I really will shut up. But what I wanted to really ask you all, I wanted to ask you how this links to the lab. I think I'm about to tell you because I don't think I can form it as a fair question, but in our current example, we have this. Our example is as general as can be, except that we specifically started, except in our example is like as general as can be, except that I'm specifically demanding that each oscillator is differing from the other by pi over 2. And I just made up that number. There's no law that it says it has to be. What we've now said is that pi over 2 is an example. We're now saying this is an example of an angular wave number whose units are necessarily radians per meter. So we're just talking about this example where it happens to be pi over 2 radians per meter. What I do want to ask you guys, I'm going to, sorry. Great. Okay, I was about to ask you guys a question, but okay, Rain's question. I don't even know how I missed it, how long ago I missed it. Sorry, I missed it. But right. Wait, okay. And I'm going to keep coming back to this question in the chat from Rain. I'm going to keep trying it because it is the key question. I'll try one more different way right now. But yeah, when you see a wave motion, when you see, like, and usually if we were all together, if ever there was a time for us to just put on all the videos, this would be the time. Because like if we were in a class right now, this is what I would ask you. To answer Rain's question, I mean, one thing is to picture like water waves. And what I'm saying is if you picture water waves, what's really happening with water waves, there's no water that's actually like gliding in towards the shore. What there is a bunch of water back here far away from the shore going up and then coming down. And just as that water's going up, then the water next to it, just as that water's coming down, the water next to it is going up and then it starts coming down. And then the water next, in other words, there's a bunch of water molecules just going like this, exactly in the manner that I'm trying to ask everybody to picture here with the springs. Or if anybody lives in Brooklyn, for example, like the fountain that used to be on all the time outside the Brooklyn Museum, if you know there's a big fountain. So if you know what I'm talking about, you do, and if you don't, you don't. But what I'm saying is what waves really are, or when you guys in lab 3, when you take that long slinky and you attempt, and I don't really know how this worked as a lab simulation, but like if in real life, if 2 people were holding 2 ends of a long slinky or a long spring or even a long telephone wire, and one of them like flicks one end and sends this pulse to the other, like one simple wave pulse, like just like a hump, a crest and trough that goes riding along. And I hopefully you all could picture that. That's an example of a wave pulse when like a bump in a string starts gliding along, or even if it's a slinky and you flick the slinky. And so I have lots and lots of movies of stuff like this. I have a whole YouTube channel, in fact, of stuff like this. Anyway, but the point is, if you picture any of those things, the key thing to picture that I'm trying to say to Rain and everybody is like what you see with your eye when you see a wave pulse is you see something move from one place to another. Like if you flick a slinky, you'll see like the bunch of metal, like a blah, 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 and what you're seeing is like a bunch of metal, like the tightly bunched little pieces like travel along. But it's an illusion. It's like another way to explain it. It's just like back in the day when the city was open and we went places and stuff, like if you look outside of diners or movie theaters or like theaters on Broadway, and like they have those crazy, and again, I have a whole PowerPoint about this I can put up on YouTube, but like if you picture a bunch of light bulbs around a sign. Here, I'll try to draw this what I'm saying. You'll totally know what I'm talking about. It's like everything. The minute you know what I'm talking about, then you'll totally know what I'm talking about. And until you do, whoever, then everything I'm saying is like gibberish. And I know that. But picture some sign like eat at Joe's, like restaurant or whatever, right? And there's a bunch of light bulbs around the sign. And if it's working properly and stuff, and you walk past the sign at night, what you see, what you think you see with your eyes, like light traveling around the sign, like glowing. I'm so bad at, right? But like it's, or, you know, it looks like light going around and around the sign or through the letters or whatever. But of course, if you stop and think about it, you realize there's no light going around anywhere. There's like a bulb that goes on and then it goes off, and then the bulb next to it goes on, and then it goes off, and then the bulb next to it goes on, and then it goes off. So what we see is lightness, luminosity moving from bulb to bulb, but there is no one light that's moving anywhere. There's just a bunch of lights oscillating in place. I'm saying anytime you, and again, I'm either oversaying it or undersaying it, but I think it's great that Rain is pushing on this. Like what I'm really trying to say here is that anytime in life you've ever seen what you think is a wave pulse, what's really going on is a collection of last example. This is what I was going to say we would do in the lab. The most clear example really of all is if you're at Yankee Stadium or Shea Stadium or whatever, you're at a game or a concert, I suppose, and anybody in the crowd, like all in the aisles, like, okay, let's do the wave, right? So you do that thing that maybe gets captured on the TV cameras or maybe not, but like everybody goes, ah, at the same time. And then over here, it goes, ah, and then down. And okay, so then if cameras are looking down at the stadium or wherever where people do this, and they do it well, it can look super cool, right? Like you have this whole ripple of like arms rippling around the stadium, and like you can track it. It's like a physical phenomenon. Like the stadium is this long around, and it takes a certain amount of time for the ripple to go around. And you can literally take bets, like, is it going to go around twice? Is it going around 3 times? And no one's going to disagree. If like once it does what it does, everybody's be like, yeah, it went around twice. Like, in other words, there's a motion that we're all agreeing that we see, the ripple of arms. And it's all formed by human beings. So there's a motion going around the stadium, and only human beings are moving. But if you think about it, the whole point of that wave in Yankee Stadium, whatever it is, it's a motion that's going around the stadium. Only human beings are moving, but no human being is moving around the stadium. That's what makes it a wave. And that wave that you do in Yankee Stadium, that's not, people think like we're pretending to be, I don't know what people think, actually. What do I know what people think? But you might think, oh, when we perform a wave in Yankee Stadium, we're like, we're having fun being human beings, like simulating as though we were a wave. But of course, it's not like really a wave because like we're human beings. But no, that is literally is a wave. Like what a wave is when you have a collection of individual oscillations that then forms this pulse that goes, and literally the perfect example, those human beings, each one of them is only moving in their small neighborhood along a y-axis. They're like going up and then coming down. That's all they're doing. But the whole phenomenon is then traceably moving through the x-axis. Like, that's cool, because what's moving is a ripple in people, not people, but a ripple. We technically call that a pulse. Like, that's a wave pulse. It's a motion, but it is not a thing moving. It's like a moving without a mover. I mean, I don't know if that helps Rain's question at all. Again, I'm going to keep, but the English of it itself is meant on the one hand to make it more clear, but I am trying to say with English, like, this is a weird thing that we even like, that we would even notice or be able to deal with as human beings. Like, it's weird. So it kind of makes sense that there'd be math that would be sort of abstract. I mean, to me, the math then makes it even better and more clear. I don't know what it'll do for all of you, like, you'll have to see, but of course we're not going to do the math of this, but this is the thing we're talking about, collective oscillations, then forming motions on their own. So my question to the class, minus Ray or to anybody, is this angular wave number thing here, like, just like angular frequency is called omega, right? Like, we have a letter for angular frequency, we call it omega, and from now on, you would put that in. Does anybody make the connection, or can anybody see from lab? I would claim that from lab 3, you actually know the letter. It's an unfortunate letter. We've used it before, but there's a letter for this angular wave number thing. There's a letter, like sometimes this letter equals pi over 2 radians per meter, but sometimes it equals pi over 4 radians per meter, or it can equal whatever. Does anybody know what letter we use for this from lab 3? Or and again, it's an unfortunate letter because we've used it in other cases in physics, but there's a letter, a variable, a constant. Does anybody know what I'm talking about? In other words, there's a fast way to write this equation. I guess what I'm saying is, so I'm about to write the equation. And I'm going to write the same thing I've been writing over and over again. The only difference now is I'm not going to write pi over 2. I'm going to put in a letter that in general allows for that term to take on any value, whether it be pi over 2 radians per meter or pi over 4 radians per meter or whatever. So I'm going to write a letter instead. If you guess the letter in advance, I'll be very thrilled to the bottoms of my soul. But I'm going to write it one way or the other. And every time I'm writing A, I could also write Y naught, same thing. But I'm specifically writing Y, right? Because all the oscillations are happening in the Y axis. But then I'm saying, yes, yes, and you beat me to it. Durkheim, the man, the myth, yes. It's like, yes. What more can I say besides yes, K? That's exact. That totally means to me, my world has just come together. I now feel like there's some coherence between your lab experience and your lecture experience. Something correct is happening, at least through the brains of, I know, more than one person. No, fantastic. K is exactly what I was looking for. And also, I commend you, because it's really unfortunate that this term is called K, because we already have so many Ks in our life. Yeah. Oh, good, 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 good. What a nice thing to say. You didn't even have to say that at all, right? I love this class. Yeah, cool. And hopefully it's about to make even more sense, or hopefully we'll go. No, what, we have time for a little bit more sense, and then we'll go. But yes, that K from lab, which, by the way, believe me, I know, when it first emerges in lab, it's even more out of nowhere than when omega first emerges in lecture. I do understand that for a while K is there, you're just playing around it, through it, trying like it doesn't look like it means anything. It's out of nowhere, I know. But since you still haven't written actually the post lab for 3, yeah, hopefully this can start clarifying what that K is this K, is the thing that we're using pi over 2 as an example thereof. It is the rate in space counterpart to the angular frequency rate in time. And this is what brings the whole thing together and turns our single oscillator into an actual wave pulse. Like, I'm going to describe this a different way in a moment, but a wave consists of many, many oscillators, and a wave, what it really, another way to look at it that you're trying to see in lab 3 is it's oscillations in both space and time. That's what's really happening in a wave, is things are going, any given slice of it is going up and down in time, but also any given spatial slice of it is going up and down in the other axis of space. Okay, all right, but okay. So this equation that you sort of see in lab 3 is what we're talking about here. It describes a wave pulse because at its root, what it really is a bunch of Y oscillators placed along the x-axis and staggered in phase by a constant amount K. So K, yes, you win for saying K. That's awesome. Now, what am I going to do with this? Well, I'm going to say we're now, the math is suddenly exciting, is one way to put it, because now we're saying, these kind of waves that we're talking about, and I actually should be clear. So what I'm writing here, what I'm saying is waves, it seems, or at least the waves that we're talking about here, require 1 dimension of time and 2 dimensions of space. They require 2 dimensions of space to describe. Like, we have oscillation in 1 dimension of space, but we have propagation in the other axis of space. Each oscillator moves up and down, but therefore the whole pulse travels left and right. right? At least in this kind of wave. Now, this is a kind of wave, so I should be clear about that. It's actually not always have to be this way, but this is technically called a transverse wave. And a transverse wave means specifically if it's a transverse wave, then it's everything that we're describing here. And this includes water waves at the ocean, waves along a slinky as in lab 3, mechanical waves. The essential property of a transverse wave is that all the oscillation occurs on one axis, and yet the propagation occurs on a perpendicular axis. And what do I mean by propagation? Propagation is the fancy word that we introduce now, but we introduce for real and for all time. Propagation on the one hand is just a fancy word for motion. Like propagation does mean travel, motion. But we introduce it now, not to be redundant, but to distinguish for all time from here on forward. Whenever we see a particle, a distinguishable item, a countable thing, like an actual discrete object that we could say, hey, that's a baseball, or that's an electron, or that's a planet. Whenever such thing travels, we call that traveling or motion. We'll talk about the motion of the baseball, the trajectory of the baseball, the trajectory of the planet. But if a pulse moves through space, and we want to constantly remind ourselves that a pulse has all the properties of a moving thing, but is not, in fact, a thing. A pulse is not a thing. A pulse is like a bundle of energy, if you like, or a bundle of information, or a disturbance in a medium. A pulse is whatever it is not a distinguishable object. So whenever a pulse is moving through space, we call that motion propagation. Like literally, propagation is the word we use from now on to mean motion of an immaterial thing. And it's really cool that we even have a word like that in physics, because it means that physics is oriented, half of the subject is about motions of these immaterial things that we track so carefully, but we never forget what they are. We give them their own word. So propagation means motion of immaterial or of pulse. Now, transverse pulse works the way I'm saying, like it requires 2 dimensions of space and 1 dimension of time. Why am I getting off on that topic? Why do I care? I mean, why do you care? Because it's expressed in the equation. I mean, the equation for the first time, if we're saying this is actually a challenging new, well, it's a provocative new area, because look, this equation has a t in it and has an x in it and has a y in it. It is referring to 2 dimensions of space, 1 dimension of time. More to the point, this equation has 1 dependent variable relying on 2 independent variables. And that is the first time that has ever happened to me at this point in a math or physics class. Like you may have done tons of other stuff, but as far as anything that anybody's been required to do to get to this point, we've actually always insisted that our equations be 1 cause, 1 effect, 1 x-axis, 1 y-axis, graph it, sucker. Like all our equations up until now have been 1 independent variable, 1 dependent variable. We have to stop here and actually definitively notice we now for the first time have a function of 2 independent variables. In this case, y is a function of x and t. That's what I'm writing there. That's important. Like that doesn't mean we can't, it's not meant to be intimidating at all. It's totally manageable, but the way to manage it is to know that that's what it is. We're now actually looking at effects that are driven by 2 independent causes, if you like, if you want to think of it. Like, and what do I mean by that? I mean lab 3. I mean that at any given moment, if you want to know the height of that pulse that you track in lab 3, if at any moment someone asks you, what's the height of this pulse? If you think about it, in order to answer their question, you first have to say, wait a second, when are you asking me? Like at what point? What do you mean the height? This thing is wiggling up and down all the time. When do you want to know the height? And then you also have to ask the person, where do you want me to look? Like where on the pulse? Because the whole pulse is wiggling. The pulse is wiggling in time and it's wiggling along the x-axis. So the answer to the question at any moment, what's the height, depends on you first specifying where on the x-axis you're looking and at what point in time you're looking. It's a function of 2 independent variables. can we like do stuff with it? Yes. Can we do calculus with it? Yes. Are we going to? Yes. Starting right now. Bear with 1 second. Okay. So again, I'm a bit lecturing at the moment. I've a bit departed from the question that I can ask, but I had to give you this information. I apologize. What I'm saying now is we're analyzing this. We now have a new way of expressing a wave pulse. We have an equation that doesn't just express the behavior of an oscillator, but now expresses the behavior of a pulse. That's what we have now. So I'm trying to analyze that equation. In fact, what I really want to do is I want to take some derivatives of that equation because I want to see how this brings us back to the differential equations. I mean, to be honest. But I'm not, before I do any calculus or anything, I have to pause and say to myself, okay, this equation is a function of two variables. I want to look at rates of change, but how do rates of change work when there's more than one independent variable? So I'm just reminding myself, I'm saying, okay, back in the day, back with regular equations that we were just starting to get more used to, if we have a regular equation like y equals f of x, if we have a regular function of one variable, then if you ever want to know what amount of rise you just experienced in that, like if you graph that equation, whatever it is, some general equation, and you ask yourself, what's the rise in this function? Well, the rise at any given moment is the run times the derivative, right? Because the derivative is rise over run. Like it's like a dumb thing to say, but it seems like a dumb thing to say, but it is true that in other words, at any moment, if you're interested in what the rise is, if you happen to know the rise over run, the slope, the infinitesimal derivative, well then just multiply that by the run and you'll be okay. It's kind of like saying, as long as you know that mass, if you know that density equals mass over volume, then it does often come up that what you're also saying is mass at any moment is density times volume, right? So it's true. It may not be interesting, but it's true. But similarly then, if that's true, I'm going to extrapolate and say, if I have a function of more than one independent variable, and I want to measure the rise in that function now, so I have a function now that's harder to draw, right? Harder to graph. I have a function where like the height of the function is dependent on height on like some z-axis is dependent on how much you crawled along the x-axis and how much you crawled along the t-axis or something, right? It's like I would require like a cube to draw this graph. But in such a case, I think it's still fair to say that the amount that you would rise up would be the total amount that you rose due to run in one axis plus the whatever was due to the other axis. In other words, we still believe in physics. Well, I'm going to write. We still believe, as we have from the beginning of physics, that any n-dimensional phenomenon or experiment or problem, any n-dimensional phenomenon is, in fact, n one-dimensional phenomena, and if anybody completes this sentence, they get the, I don't know, the spiritual prize of a lot. I mean, you get like the home game. If I'm going to say because this is a harkening back to physics 203 now, but I want to remind us that any n-dimensional phenomenon, so like, for example, any seemingly two-dimensional problem that you encounter, what we believe in physics from Galileo is if you think you're facing a two-dimensional problem, what you're really facing actually is two one-dimensional problems that are occurring. And there's two words I'm going to say if people don't interrupt me. When you think you're looking at a two-dimensional problem, you're really looking at two one-dimensional problems which are occurring simultaneously and yet independently. And that is a key. I'm going to write occurring simultaneously, like at the same time, yet independently, as in not affecting each other, not knowing that the other one is there. Each one contributing an amount that would be the same whether or not the others were also contributing amounts. In other words, there's no interaction among axes. And that, we believe that we've been doing vectors on that basis from day one. And we're going to still believe it now, even as our vectors get treated by calculus. I still believe that what happens on the X, like basically what happens in Vegas stays in Vegas, as long as by Vegas you mean the X-axis, which I'm sure is what that expression always had in mind. We are literally saying what goes on the X-axis does not affect the Y-axis and vice versa. Therefore, and I'm just talking, but therefore I'm saying if we have something like y equals a function of x and t, then dy is going to equal this. It's going to equal the sum of the d's that came from both the x and the y axes. The whole is equal to the sum of its parts. So it's going to be like this. And again, I really do apologize. I didn't actually mean for this to happen, but just to be clear, I am just talking right now. I mean, this is all the material we have to do, and I'm trying to explain and clarify it, obviously, but clearly there's not a question that I'm asking yet for a while, and I do apologize for that. But that is what, but it's not a digression. This is the material. I just can't make a question out of it quite yet. But so this is new. I want to be very clear that what I'm saying right now is 100% lecture material, and of course you can just get it later from the YouTube or whatever. But you will want to get it because this is what I'm saying now. What the heck is even in my mind the first time you've ever heard it. Like, and if you have heard this some other way, that's a good advantage. That's nice. But I'm not assuming that this is not a review of something you already know. This is me now explaining or trying to that I'm saying from now on, if we are going to deal with functions of more than one variable, which physics is forcing us to do because we want to look at a phenomenon that takes place for which like some result in one axis of space is the result of both coordinate in another axis of space and coordinate in time, like that. So mathematically, we're forced now to look at a function of more than one variable, and we got to do calculus because we're physicists. So the new calculus principle that I'm saying is from now on, if you have a function of more than one variable, then the full derivative of like the full rate of change of the whole function is the sum of its individual rates of change, or what we're going to call partial derivatives. So this is an introduction. This is a new idea. Sorry, forget that. Okay, so what I'm saying, wait, it's 120. All right, I will try to end with some kind of question, even if it brings us next time. Oh, well, no, I can't guarantee. Well, yes, I can. I'm just trying to say now. So this again, it's not a digression, but this is like a math sidebar. Like we just hit a new equation in physics. Like if we're keeping a list of equations, like our new equation now is y equals a cosine omega t plus kx. Like first we just had omega t, then we had omega t plus some number like phi. Now we're saying, what if that number is actually a step function that we apply to a whole other axis? So now we have plus kx. It's a new equation. This new equation we're about to analyze in physics terms, but in order to do it, we have to recognize now there's a thing I'm introducing. a thing called a partial derivative. From now on, there's something called a partial derivative, where we use this funny symbol here, here, here. It's like a little d. And remember, we went from deltas to little d's when we went from small but finite intervals to infinitely small intervals. Like that's when we shifted. It used to be, we used to have delta y over delta x was like slope, but then we shift that to dy over dx is like slope over an infinitely small run. So we call that derivative. Now I'm switching, I'm introducing a new thing called like this other symbol yx. This symbol, it looks like a lowercase delta. It's not. It's actually not even a Greek letter. It's just some weird symbol that's just drawn like that, like a backwards 6. Some people have told me it's Celtic. That may be true. I don't know. But how we read this new symbol, it is a new symbol that I'm introducing now. How we read it, we literally just read out we say the word partial. It's called partial, like on a keyboard or anything. Like the first thing was called a delta, then that other thing was called a lowercase d, but this thing is called partial. So if I see partial y over partial x, like right here, what that means is the rate at which y changes as a function of x. Like it literally means, it means the rate at which any run along the x-axis will produce rise along the y-axis. And it is totally independent of anything that might go on the t-axis. In fact, the whole point of it is, the whole point of it is that you can measure it or picture it by standing at any t value you want and just walking around x and seeing what happens to y, right? So I'll write this. Super important thing, even if, again, even if I don't get to a question, I have to say this. And we'll wrap up momentarily. But so I'm introducing now, we have like slopes, which are rates of change over finite intervals. Then we have derivatives, which are rates of change over infinitesimal intervals. Now we have partial derivatives, new concept. Partial derivative is a derivative. It's totally just is a derivative, which means a slope, a rate of change over an infinitesimal region. That's all it means. But we use partial derivatives whenever we're looking at some kind of dependent variable that's driven by more than one independent variable. If, in other words, multivariable functions, what we're talking about here is multivariable calculus. If you have a multivariable function, then it's okay and proper and necessary to examine partial derivatives, which means the derivative of the dependent variable with respect to each or any of its constituent independent variables. When we look, and I'm just saying in English now, we're about to do our final thing mathematically and be done for the day. But what I'm saying in English is the concept of a partial derivative is a rate of change with respect to a certain variable, holding or assuming or pretending, treating all other potential variables as constants, right? In other words, this is totally the thing you do in lab 3. Like when you in lab 3, or when you look at when you produce wave pulses and then you took videos of them and then you analyze the data of the videos, you have you make two different kind of graphs, I think, in principle in lab 3. You can either look at one frame of the movie of a wave pulse. You can look at one frame and take data, ordered pairs, points, data points, and make a scatter plot. You can look at one frame in time and see how y varies as a function of x, right? So that, or you can take one slice, one value of x, and run a movie watch what y does up and down as time rolls, right? You can either look at how y changes with respect to t, and when you do that, you're just artificially holding x constant. You just pick a place and you look at the movie, or you hold time constant. You just pick some random time value, and you hold it still by looking at a frame, a frozen frame, and you measure y versus x in that frame, right? That concept that you're doing in the lab, which is the whole point of an experiment, just holding everything constant except for two variables at a time. We're saying mathematically we have the tool to do that. We have the tool to do that. Sorry, I totally just got, and it's called the partial derivative. The partial derivative looks at a rate of change with respect to one variable at a time, and in so doing, it pretends all the others are constant. So what I'm going to do now, actually, because we're totally running out of time, I'm just going to, but I do want to end with something mathematically. Here's what I'm literally saying. Well, I'm going to ask you to take two partial. I'm going to take the equation, and I'm going to take two partial derivatives in time, and I'm going to take two partial derivatives in space. If you can beat me or whatever, or put anything into chat, like points, but since we're totally running out of time, I'm just going to do it here and let us go at that. But the goal is to take this equation now and differentiate it with respect to time twice, and space twice. So I'm just going to do that, and then we're done. So here we go. But you'll see why if you don't already. I know. So I'm first taking the partial derivative with respect to, oh, sorry, that's not the, this is a different K, by the way. It's the K from lab 3. It is not the K of Hooke's law. And I know that's super annoying, but it's just true. So. So far you see what's happened. So I took two derivatives, but I treated t as the variable. I pretended x was like a constant because I'm not differentiating with regard to x. X is actually a variable, but I'm holding it constant when I do a partial derivative. Now I'm going to do the same thing for the x's, and then I'm pretty much going to shut up and say goodbye. We'll just leave it there. But maybe you can beat me, but I'm going to do the same thing for the x's now. That is time. We're going to end right there. It doesn't seem very conclusive. I'll say that where we're going to start next time. I'll tell you right now where we're going to start. The very next question is, can I relate those two partial derivatives? I mean, the answer is yes. And when we relate them, we get what's called the wave equation. And this really will help you with lab 3, whether it's the post lab or the regular. But where we're going to start next time in 2 days is just, can you, given what I just did, then what is the relationship between second partial derivative of y with respect to x and second partial derivative of y with respect to t? That's what we do next time, but we'll end right there. Sorry I didn't ask more questions or do more points. I'm going to give you back your portals and open up the portal for today because a lot of people did, but I'm going to go right now because I have to, and you all are awesome, and electron bless America. Oh, wait. Oh, okay. I see that. Wait. Okay. Fair enough. And I see what's in the private chat. Anybody already? I got it. And I'm sorry, I will check it, but I'm not going to right now. Got it. Okay.